So this is section 5.6, exponential models and applications. So now that we've learned about exponential equations, now we can understand how to apply it to our world. So we're going to do examples from time is money, radioactive decay, and then population models. So the first one is time is money. So we're going to do an example of this. So it says, suppose that you deposit $10,000 into a savings account today. Determine the future value A of the deposit if it earns 5% interest compounded monthly after. Okay, so let's highlight all of our important information. So they give us a deposit of $10,000. Determine the future value of A, 5% interest, and compounded monthly. Now, if it says A, this kind of actually reminds us of, we're doing A first for 20 years. The formula that we're going to use for this is A equals, or A of T equals P1 plus R over N raised to the N times T. So this is actually going to be the exact same information or same problem we did before, but now we're going to turn it into also logarithmic or exponential form to solve for when the balance reaches the amount that we want. So we're trying to find A, so we don't know what it is. They give us time, so our time here was 20 years, right? Our initial deposit was $10,000. So let's label these. So our time was 20. Initial deposit was $10,000. And then they said that our interest, so what was that? That's our R, right? So that would be 5% divided by 100. Well, 5 divided by 100 is 0.05%. And then our N was compounded monthly. So that means our N is 12. And then, so now let's put it all into our formula. So 1 plus R is 0.05. Make sure you divide by 100. If you don't, then it'll make your information incorrect. And then we do N. So N was 12 and our time was 20. Okay, so now we just evaluate this. So I'm going to do in the parentheses first. So 0.05 divided by 12 plus 1 gives me 1.004166666 raised to 12 times 20. So 12 times 20 gives me 240. So let's evaluate that. Raised to the 240, I get 2.7126400502. You multiply that by the 10,000. So A is going to be 27.26. So we know that A of 20 will give us $27,126, and then I'm going to round it to the 10th position, so it'll be 4-1 because we have a 5 here. So if it's 5 or greater, it's going to round up. So we know that in 20 years, it would be 27,000. But then when will it reach 50,000? So this second question is asking, so when will our balance reach 50,000, or when will it be worth 50,000? So what is this asking? It means that we're trying to find time. We don't know what the time is this time. So, that's what's funny. So we know that our A of t, that's what we're looking for, is going to be equal to... so they actually give us our A this time. So before I even write the equation, I'm going to label all my parts. So if they said 50,000, 50,000 is my A. And then my initial deposit, again, is the same amount. So that was $10,000. My R is still the same. It's going to be 0.05. We don't know what time is. That's what we're trying to find. And then our N is still going to be 12. So this was A and that was B. So this is finding what the amount will be, finding time. So now I can set up our equation. So it's going to be 50,000 equals 10,000. 1 plus 0.05 divided by 12. 12 to the t. Okay, so one thing that's super easy that we can do here is to make our solution easier to solve. I can actually cross out my zeros to make it easier. So if I cross out 4 zeros here on both sides, since I have 4 on both, it'd be 5 divided by 1. So 5 divided by 1 is just 5, which makes it really easy to solve this. And then 1 plus, so let's do the brackets now. So 0.05 divided by 12 plus 1 gives me 1.0041666667. And then we have 12 to t. So I can't really solve that yet because I need to simplify it. So how do I do that? Well, one of the things we have, and make sure in this step what we need to add in is the ln or the log. I'm just going to add ln. So now if we notice, we have an exponential equation. So what do we do if we have an exponential equation? What's going to happen is it's going to want to go to the front of our ln or our log. So ln of 5, now it's going to be 12 times t, ln of 1.0041666667. And then what can I do? Well, I want to get t by itself because we're solving for t, right? Well, one of the things I can do is I can divide the 12 and I can divide the ln out. So it's going to take that out. And now if I do that on one side, I can do the same thing on the other side. So 12 ln make sure I didn't do too many 6s there. Let's just double check. Yeah, it's 4 6s. So now this is gone, and what's left on the right hand side is a t. So now we can just simplify. So in my calculator, I'm going to put these values in. So ln of 5, we're just going to do the ln. And then 12 times the ln of 1.0041666667. I get 32.255. So 32.255. I don't know how many sig figs. I'm just going to go to here. So t equals 32 let's do 3 years. So in 32.3 years, the balance will reach $50,000. So this is our answer. So for this problem, this is how you would solve it every single time. You can use the log or the ln. Either one will work. I just decided to do the ln here. And let's do another problem. So the next one's going to be on population. Okay, so for this problem, we're being asked about the population. According to the city's census, the population of City X in 2020 was 500,000 people. In addition, the population of the city was growing at a rate of 2.5% per year. Assuming the growth rate continues, the model P of T 500 times 1.025 raised to T minus 2020 represents the population P in the thousands of people per year T. According to the model, what will be the population of the city B in 2050? And according to the model, in what year will the population of the city double in size? So for the first one, they're asking us, what will the population be? So that means we're trying to find P, right? Okay, so we're going to do the first one. So if we're trying to find P, we don't know what it is because they're asking us what the population will be. And they don't give us the time, right? Well, we have to find what the time is. They give us a date, 2020, and we also have another time that's given in the actual second question is 2050. So that means our time will be 2050 here minus 2020. And we'll do that in the problem. And then, so we have a lot of other pieces. Now we can put it into our problem. So we're trying to find P. So P of 2050. And they give us 500 and 1.025. 2050 minus 2020. So really we're just taking the time that they give us. So 2050 minus 2020 would give 30 years. So that means it's going to be rewritten as 500 to the 30. So now we just do 1.025 raised to the 30. And we get 2.097567579. Then you multiply that by the 500. So I'm getting this. So that means if we write this in the whole number, so P of 2050 is 1 million. It's a lot of people. And then the second question is asking us, what would it be if it was to double in size? So that means if we double, that means it's going to be times 2. So if I do 500 times 2, that means we get a 1,000. So it's going to be 500 times 2 gives me 1,000 since we're doubling in size. So now we just calculate using that number, using the same years they gave us. But then again, we don't know what time is, right? We need to find out what it is. So we can't use a 2050 because they're saying what year. So P of T is equal to, but now we know our population is going to be instead 1,000. The original goes here. T minus the original. So our original was 2020. So now what I can do is we can just divide everything. So to make it easy on myself again, we can easily just cut out some of our zeros. So that makes my division super simple. So then I get 10 divided by 5 is 2. Now what I want to do is add the ln. So ln of 2, ln of now we want to bring our exponent down. But now I want to get t by itself, right? So I'm going to divide this guy. I'm going to move that guy over. So now it's gone. And then I have the t minus so then what can I do? Well, I just want to move it to the other side. So we're going to move this guy over here. And then when you move it to the other side, remember, it becomes positive. So now it's plus 2020. Yeah? Now we can just do the math for that. So let's see what happens when we add them together. So we'll do the ln of 2 over the ln from 0.025 plus 2020. So I'm getting t equals 2048. So that means our year will be 2048. So in 2048, our population will be double the size. So that's how we do the population. Now we'll do a couple of problems on decay. Okay, so in this question, we're looking at radioactive decay. So the question asks, the half-life of a radioactive substance, substance X, is 15.6 days. Suppose that a researcher has an 80-gram sample of a substance X. The amount of A of T in grams of substance X remaining after T days is then by A of T equals A to the 1/2, or times the 1/2, to the T over 15.6. So when will there be 60 grams of a substance left, and when will there be 5 grams of a substance? So both of them are going to be actually asking the same exact question, but instead of, like in your textbook, they gave you in seconds, we're going to be looking at days. So that's what our unit is here. So we're looking for time. And in both of these examples, they give us A. So let's do A. And let's write down our equation. So A is 60 equals 80. This should be 80, isn't it? Yeah, this should be 80. 80 to the 1/2, or times 1/2, T over 5 points, or 15.6. So we're trying to find T. So again, what I can do is I can cancel out my zeros here and divide by what we have. And so we get 6 over 8, 1/2, and t to the 15 over 6. So we know that 6 over 8 can reduce. So 6 over 8 gives me 3/4, or 0.75. I'm going to put it in the decimal because that's easier. So 0.75, and I make 1/2 0.5. T to the 5, 15 points. I keep saying 5. Huh. And then make sure we put our ln or our log. And then we have an exponent, so I want to move the exponent to the front. So the next step we're going to do in 2 different parts. So the first thing I always do is I divide the ln out to get rid of it. So when you divide on one side, you have to divide on the other. And then the next step, we have t over 15.6. Well, I don't want the 15.6 there anymore. So one of the things we did, like we did, if it was an LCD, we did was we multiplied it. So I'm going to multiply the 15.6 out. To get t by itself. So now we can solve for this. So I tend to always put the L, I do the ln calculation, then I multiply or add. You can write it the other way too. I just find it easier. So ln of 0.75 divided by the ln of 0.5 times 15.6. And I'm putting this in my calculator. So I'm finding that it's going to take, let's see, I get 6.47. So t equals 6.47, and the next number next to it was 4, so that means I'm not going to round up. So it's going to take 6.47 days for there to be, what do we start with, 60 grams. So it's going to take 6.47 days for it to turn to this amount in the sample, 60. Now, the second one, they said that our A was 5, so we're just going to use 5 instead. So 5 equals 80. I'm going to turn that into 0.5 because it's 1/2. It's easy to just do. Well, since I don't have another 0 next to the 5, I'm just going to divide it as is. So 80. And remember, the 0.5 is the 1/2. So 5 divided by 80 is what? I'm getting 0.0625. Now, since we have an equal sign, this is a type 2. So again, I'm just going to put the ln or the log here. Then we can't have any exponents, so we move our exponent to the front. So like the last one, we do the same exact thing. Divide the ln out. It's a lot of repetition at this point. And then I got rid of that, so now I have to get rid of the 15.6. So like we did last time is we multiplied it. So then our t will be what? Let's see. So the ln of 0.0625 divided by the ln of 0.5 times 15.6. I'm getting 62.4. So I'm getting 62.4 days. If you got 62.38, it would be 60, you just round up. So this is our answer. And now we're going to do one more decay problem with a little bit of different setup, but it'll be along the lines of this. Okay, so this problem is going to be solved the same exact way as we did the last one. But of course, it's just using different values. So the half-life of uranium-238 is 468 million years. Suppose a researcher has a 20-gram sample of uranium-238. The amount A of T in grams of uranium-238 remaining after T million years is given by how long will it take until only 0.5 grams of uranium-238 will be left in the sample? Okay, so they give us our A. Our A is 0.5 grams, so we're going to put that here. I'm going to put grams here. And then they give us 20, and then they have all our other values here. Okay, so I'm just going to divide the 20 out. I'm going to add my ln. And then, so 0.5 divided by 20 gives me 0.025. So now I want to get T down because it's in the exponential position. Now we can divide the ln out. So you can see it's the same solution as last. Or the solution plan. And then I want to multiply. I'm just going to show that step here. I'm going to multiply the 4,468 out. So I know I'm doing two steps at once. T. So now we can solve. So the ln is 0.025 divided by ln is 0.5 times 4,468. So I'm getting 23,778.37473. So if it's in million years, that means it's going to be 2362.65 million years. Not 65. It's going to be So this is our answer. So this is how we solve models and applications for 5.6.